vectors u and v, typically in 3 dimensions, although of course I will remind you that, especially if you take 22a, we can think of vectors in higher dimensions. So u is u1i plus u2j plus u3k, or just the components u1, u2, u3. V is the same. There's some angle between u and v. And then if you want to calculate the dot product, there's 2 different ways. It's the magnitude of u times the magnitude of v times cosine of the angle between them, which is not the way we usually calculate it. Typically, we just multiply the components together and add the results. So u1, v1 plus u2, v2 plus u3, v3. And then analogously, there's also the cross product, which is a way of multiplying vectors together. And we'll point out, sorry, let me cat out. Okay, you're free to go. That when you do a dot product, you do just get a scalar, right? So this quantity here is just a number. Whereas when you do the cross product, u cross v, which is the magnitude of u times the magnitude of v times sine of the angle between them, times the vector n, which is perpendicular to u and v via the right-hand rule, that this is a vector, right? So this, sorry, I've written that here, right? So you calculate this by doing the determinant of the matrix with I, j, and k, and then the components of the first vector, and then the components of the second vector, and then you get this whole mess here. And this is a vector. So when you dot 2 vectors together, you get a number, also known as a scalar. And when you cross 2 vectors together, you get another vector that is perpendicular to both of the vectors you crossed. Okay, so that's the basics again. And then, of course, we can use this formula if we want to find the angle between 2 vectors. I suppose if you were crazy, you could also use this formula, but no one does it that way. Right? If you ever ask about finding the formula, the angle between 2 vectors, we always use, oh yeah, I'm going to take the dot product equation and solve for cosine theta and then solve for theta. All right. So let us look at some other stuff that is related. Yeah. Let's talk about lines and all that jazz. So lines in parametric form. So in 3D space, we don't have nice equations, right? We don't just get y equals mx plus b. Because in 2D space, you can just say, okay, a line, you need a point and a slope. What form did you say? So I'm looking at the, oh yeah, in fact, for those of you that might have come in after I posted the link, here's the link. And actually, let me just share my screen so I can show you guys. Sharing the screen is that green button there. So I'm just looking at down here, over here, lines in parametric form. I'm basically looking at all these 4 or 5 handouts. And I'm kind of going to walk through most of them there. Okay, so lines. So we need the same kind of idea for a line in 3 space, but you can't just say like a slope, right? Slope in 2 space or 2 dimensions is like change in y over change in x, but in 3 dimensions, you've got kind of 3 different directions to go. So you can't just say it's like the change of one thing or the change of another. Basically, we need to define a line in 3 dimensions. We need a point, and instead of a slope, we need a direction or a vector. So let's look at this example. So let's find the equation of the line through these 2 points. And 513 and 651. So maybe, right, maybe the line looks like this. Here's this point. Here's this point. So here's what we need to find. We need to find the vector through the points. So actually, I guess you don't need to find the vector. I often like to find the vector. So I'm thinking about, right, the vector from here to here, even though it's totally not absolutely necessary, right? That vector is going to be 6 minus 5 is I, 1i, 5 minus 1 is 4j, 1 minus 3 is negative 2k. You don't actually need that, but it's fine. So the idea basically is you want to write three equations, which are the parametric equations. And I'm just kind of thinking like, you can pick either one of these to be your starting point. I'm going to pick this one. So this is going to be t equals 0. And then the next point you have is typically at t equals 1. And so what you want to say is that x, y, and z are all functions of this extra parameter t. So at time equals 0, time t, I mean, I'm thinking time mostly. In fact, the way Grant has kind of written this is, imagine a particle traveling from left to right at constant speed. What happens to the x, y, and z coordinate at each unit of time? So if we start here at time 0, 1 unit later, x has gained 1 unit, y has gained 4 units, and z has lost 2 units. So I know I need x to have a 1 times t, y to have a 4 times t, and z to have a -2 times t. But then I also need the starting place to be correct. So I need x to be 1t plus 5, y to be 4t plus 1, and z to be -2t plus 3. So this will get me the right equation of the line, because at time equals 0, you'll get the point 513. And then every time you increase t by 1, you'll just move in this direction, right? If t is 1, I'll get 6, 5, 1. And if t was 2, I would get, I don't know, it's not to like do the math. If t was 2, I'd get the point 7, 9, -1, right? Which would be this same vector, just right that much further. So this is the equation of the line. I suppose I could be a little bit more specific. So right, the equation of the line is given by this. And then the domain of t here is everything. So t can be any real number. T is an element of the set of all real numbers. So we can either describe a line parametrically like this. Oftentimes people write these as functions of t. So someone might write this as, instead of writing it like this, they might write the line is given by x of t equals 5 plus t, y of t equals 1 plus 4t, and z of t equals 3 minus 2t. I feel like it's usually more standard to write the constant part first and the t part second. Doesn't matter which way you do it. The way I always kind of remember it is the point should be the constant part, right? So if it goes to the point 513, you should have 513. And then the t part, the coefficients of t are just the coefficients of I, j, and k in your vector. So you can describe a line this way, or you could literally say the line is given by, it goes through the point 513 parallel to the vector v equal to I plus 4j minus 2k. We use the word parallel as a shorthand for in the direction of, right? If things are parallel, they're in the same direction. You could also write this, and this is going to be a notation that we start using in chapter 13. Man, sorry, I just went pee before class started. I have to pee again. I'll try and hold out for a minute or two here, but I'm going to have to take a pee break in a moment here because I'm old, clearly, is what the problem is. So we can also write this like this. R of t is a vector. So this is a vector function, basically describing the position of your equation. Or yeah, sorry, I feel like I'm saying this kind of terribly. So we can write this as the point 513 plus t times the vector 1, 4, -2. So this is your initial point. And this is your direction. Right, this is just, right, the x coordinate is 5 plus 2 times 1, sorry, t times 1. The y coordinate is 1 plus t times 1. the z coordinate is 3 plus t times negative 2. Same idea. Yeah. And there's lots of ways of writing this. This is somewhat standard notation. I might write it also like this. I often like to write my points and vectors as columns. So you could write this as 5, 1, 3 plus t times 1, 4, negative 2. Basically, you should get comfortable writing vectors whichever way your teacher wants you to write them, is the real truth. Yeah. So let's look at some other things about lines and planes. What if I want to find, say, where does this line, so where does the line given by, what have I got here? X equal to 1 plus 2t, y equal to negative 1, and z equal to t. Where does this line intersect the plane 2x plus y minus z equal to 5? Whoops, plus y minus z equal to 5. So here's what I would do. I would just throw all of this stuff into that equation there. So plugging all of these things in, we end up getting, let's see, 2 times 1 plus 2t plus y, well, sorry, y is negative 1, apologies, minus t, that's going to equal 5. So then we're going to solve for t. So let's see, I got 2 plus 4t minus 1 minus t equals 5. I'm sure this was designed to be, oh, maybe not. Let's see, 4t minus t is 3t, 2 minus 1 is 1. Subtract, so 3t equals 4, so t equals 4/3. So plugging that in right here, we're going to get that x equals, let me just write the point. X is going to be 1 plus 2 times 4/3. Y is going to be negative 1. Z is going to be 4/3. So the point of intersection is, let's see, 8/3 plus 3/3 is 11/3. Negative 1, 4/3. That is the point where this line intersects this plane. I should point out, a line and a plane in 3 dimensions don't have to intersect, right? You could totally have a line you could have a plane kind of sitting flat and a line that was totally like parallel to it. And really parallel, like it could be parallel this way, or it could be coming more out at you like this, right? But if the line is in a plane that is parallel to that plane, then they're never going to intersect. And if that happened, if you tried to solve that equation, you would get no solution. Okay. So I'm going to go use the restroom real quick. I'll be right back. Sorry, I was gonna leave you with a question, but I just need to pee. I'll be right back. Okay, much better. So let's go ahead and look at the following. How to tell if lines are parallel or perpendicular or skew. Or I guess intersect. So I think we all know what parallel means, right? The lines are in the same direction. So parallel lines, same direction. Never intersect. And the way that we can tell lines are parallel is essentially they're going to have the same vector part, right? They're going to have the same direction, meaning the same vector. So for example, I could tell that these lines, so line 1 given by the parametric equations, x equal to 3 plus 2t, y equal to -1 plus 5t, and z equal to 4 minus 3t, and the line x equal to 7 plus 4t, y equal to 6 plus 10t, and z equal to 8 minus 6t. These lines are parallel. And I can tell they're parallel because this line goes in the direction of, let's see, I'm just looking at the coefficients of t for my direction. The direction is 2i plus 5j minus 3k. Here, the direction of this line is 4i plus 10j minus 6k. But these directions are just multiples of each other, meaning they're in the same direction. Right? This vector, I should say this vector, is just twice as long as this vector, but they still go in exactly the same direction. So these lines are parallel. That's how we can tell. Yeah. So if lines are not parallel, there's two options. They either intersect or they don't, right? Those are the two options. If they don't intersect, they're called skew. So when I think of skew lines, I'm trying to think if there's something in the room that I can point to that you guys can see. So let me see here. Trying to think of an example of a thing. Okay. I don't have anything really like long and straight here. I have a ruler. Here's a ruler. Okay. You guys can kind of see my ruler. It's not, I wish I have a different color ruler. No, maybe. All right. So let's pretend this ruler is pointing in that direction. Up and away. You guys can kind of pretend like you can see where that's going. And then there's the line that's in the direction of this. And so like this is up here. Or you guys can't really see that. Let me do this. Okay. This line going that way. This line going up that way. They don't cross, right? Even though they might look like they cross to you because you can't see the third dimension so well. They do not cross, right? This line is very much in front of, right? Here's my hand in between them. This line here. These lines are skew. They're not parallel, right? They're not going in the same direction. They're going in different directions, but they don't actually intersect each other. That's what it means for lines to be skew. They're not parallel and they still don't intersect. Typically, the way I also kind of think of it is if you've got two parallel planes, right? You could have a line going this way in this plane and not that direction, like any other direction in this plane. Clearly, those lines are never going to intersect because the planes are parallel and the lines are contained in the planes, but the lines aren't actually parallel to each other because they're going in different directions. Skew. So how can we tell? Well, let's take a look at these lines. So let's say I've got this line, L1, given by the equations. I like to write them this way. X1 equals 3 plus 2t. Y1 equals -1 plus 4t. And Z1 equals, what do we got here? -3 plus, sorry, 2 minus t, apologies. Well, that's smart, yeah. Good job. And then the second line, if you're going to see where lines intersect, you typically want to use different parameters for each of them. So the second line is going to be given by the parametric equations. X2 equals 1 plus 4s. Y2 equals 1 plus 2s. And Z2 equals negative 3 plus 4s. Clearly not parallel, right? The direction of this line is the vector 2, 4, negative 1. The direction of this line is 4, 2, 4. Definitely not multiples of each other. So the question is, do they intersect? So if they intersect, we can find a t and an s where x1, y1, and z1 are equal to x2, y2, and z2 for those values of t and s. So let's check it out. Sometimes they try to make it super obvious so you can guess them. I couldn't guess it. I mean, I know what the answer is here, but usually you're not going to guess stuff. So let's set the x coordinates equal to each other. So 3 plus 2t equals 1 plus 4s. And typically what you want to do is you want to solve for one of these variables. So I'm going to say, I don't know, it's probably going to be easier to solve for t. So 2t equals negative 2 plus 4s. So t equals negative 1 plus 2s. Great. Now I'm going to set the y's equal to each other and plug that into the equation. So I'm going to have, for the y's, negative 1 plus 4t equal to 1 plus 2s. I'm going to plug this in for t. So negative 1 plus 4 times negative 1 plus 2s equals 1 plus 2s. So solving for s, let's see what we get. Geez, gotta do some algebra here. Negative 1 minus 4 plus 8s equals 1 plus 2s. I'm going to have 6s equals 1 plus 1 plus 4. So it looks like I'm getting s equal to 1. Great. S equals 1, I'm also getting t equal to 1. Okay. So now I have to plug in and make sure it actually works for the z coordinates, right? Because I basically just used these two equations and found the place where x and y have to be the same, right? So solving these simultaneously should work no matter what, meaning I will always be able to find a point. I should be almost always be able to find a place where two of the coordinates match. Right? So if s is 1 and t is 1, x is 3 plus 2, which is 5, 1 plus 4, which is 5. Y is negative 1 plus 4, which is 3, y is 1 plus 2, which is 3. But they might not work for the third coordinate because we didn't use that. So the test to see if it actually is the place where they intersect is then to plug it into the third one and see if they're the same. So if I plug in 1 for t and 1 for s, I get 2 minus 1, which is 1. I get negative 2 plus 1, which is 1. So check. They do intersect when t and s are 1, which is at the point x, y, z equal to 5, 3, 1, which I think is the point from one of the previous problems. Okay. So that's kind of neat. So let's look at another example just to see the other thing that can happen. So I was like, why did I remember teaching this stuff last year? I definitely taught 21C last winter. And I was like, I really don't remember any of this, like three-dimensional stuff. And I remember it was because I was actually like, it's when I was in the hospital with my back infections. I was like, oh yeah, I didn't teach this stuff last year because I wasn't teaching it. Let's look at another example. Let's say we've got these two line equations. So those are the same equations. The first equation is the same, so I'm going to kind of cheat and just change the second one so that I don't have to do all the writing again. So the first line is still the same as the first line over here, but the second line, this is why it's good not to write over your work. You're going to try and use it again. So the second line is going to be different though. So the second line this time is given by, what do I got here? X2 is 3 plus 3s. Y2 is, where'd you go? 2 plus s. And Z2 is negative 2 plus 2s. Do be careful. If you're like me, your s's look a lot like your 5s. So make sure your 5s and s's look different. It's easy to get them jumbled up. Or use a different letter. Use K or R or something that's not S. But T and S are kind of pretty standard parametric variables. So that's what you'll usually see. So same process. We're going to set this equal to that. So 3 plus 2t equal to 3 plus 3s. 3's cancel. You get t equal to 3 halves s. Plug that into the equation for the y's. So we're going to have negative 1 plus 4t equal to 2 plus s. Plug in 3 halves s here. So negative 1 plus 4 times 3 halves s equals 2 plus s. So negative 1 plus 4 times 3 halves is 6. S equals 2 plus s. So 5s equals positive 3. So s equals 3/5. And then we can go back in and see what t is going to be. T is going to be 3 halves times 3/5, which is 9/10. So here's the thing. You don't need to check this in the first two. It'll work in the first two. We use the first two equations to get these values. You could, right? And I don't really want to, but if t, let's just do it in the first one just to see if t is 9/10, you get 3 plus 18/10, which is 30/10 plus 18, which is 48/10. And if, which is 24/5. And if you plug in 3/5 here, you get 9/5 plus 15/5, which is also 24/5. So what I'm pointing out is you don't have to check that it works for x and y, because it does. You have to check that it works for z. If you plug in z, z1 is going to be 2 minus 9/10, which is 11/10. And z2 is going to be negative 2 plus 2 times 3/5 is 6/5. And negative 2 is negative 10/5 plus 6/5 is going to be negative 4/5. These are not the same, which means the lines are skew. They're not, oh, I should have said they're not parallel, right? They're not parallel, right? Because the vector here is 2, 4, negative 1. The vector here is 3, 1, 2. Clearly not multiples of each other. Not parallel. They don't intersect, so they got to be skewed. So that's how you tell if lines are, that's how you can tell what is happening between two lines. They either have to be parallel, intersect, or skew. Not parallel. And then, so if they're not parallel, they're either skew or they intersect. So we check to see if they intersect, and if they don't intersect, then they're skewed. Good times. Right. So now for the fun stuff. Stuff I've been waiting to get to. The distance between things. Points and lines and planes. Oh my. And this is where we'll definitely finally get to answer those questions. Question, where'd you go? I had you written down somewhere. I did really, it's literally like the page is turned over right here in front of me. Yeah, distance between a point and a line, or a point and a plane. So let's do a point and a line first. All right, and I'm going to try and use the same sort of variable naming setup that your book typically uses. So let's say I want to find the distance from the point S, which will come, so the point 1, 2, 3, which we'll label as S. Sorry, a little burpy here. To the line L, given by the parametric equations, x equal to 2 plus t, y equal to 2 minus 3t, and z equal to 5t. And while we don't have to draw a picture, it can be helpful to draw a picture. You can see what's happening. So here's my line. And here's my point. Let's draw a little further over here. And I'm trying to find this distance. So we're talking about the distance between a point and a line. You know, you're talking about the perpendicular distance. The problem is I don't know what that point is there. Closest to the point that's not on the line. That's okay. So this point here is 1, 2, 3. I do need a point on the line. You can pick any point you want. The typical choice is going to be letting t equal 0. So if I let t equal 0, I'm going to get the point 2, 2, 0. And then you could also pick another point. You don't really need to, though. Another point over here would be when t equals 1. It could be the point, let's see, 3. Yeah, I really don't. 3, negative 1, 5. You don't really need that point, though. You just need the vector from here to here. But you can just see the vector is going to be 1, negative 3, 5. Right? Because you go over 1, negative 3, 5. All right, so I'm trying to find this distance here. I'm going to draw the vector from P to S. I'm also going to draw the vector V. And this is the angle theta. So then you have to ask yourself, okay, do I want sine of theta or cosine of theta to find D? Well, I want sine of theta, right? Cosine of theta gets me this side over this side. Those are not the sides I want. I want that side. So I'm going to say that, and I'm saying D is the length, not the vector, but we're kind of gonna abuse notation just slightly. It's all right. So I'm going to say that, do I have enough room here? Yeah, I think I have enough room here. So I'm going to say that sine of theta is equal to D divided by the magnitude of PS. Right? Sine of theta is opposite over hypotenuse. D is the length of the distance there. The magnitude of PS is the length of that vector. So then check out what I'm going to do. I'm going to multiply both sides by PS so that D is equal to the magnitude of PS times sine of theta. And then I really, really wish I had, well, I know I'm looking for a cross product, right? I know once I've got sine of theta means cross product. Cosine of theta means dot product. So I also need this vector as well, right? Because to get the cross product, you need the magnitude of one vector times the magnitude of the other vector times the sine of the angle between them. So I need the magnitude of V but I can't just multiply by it. I also have to divide by it. So look, I can say that D, the distance between the line and the point, is equal to the cross product. I really should say the magnitude of the cross product, V cross PS, divided by the magnitude of V, where V is a vector that goes through the line, or V, you can say V is a vector that is parallel to the line. And V can be anything, right? I'm going to take the vector 1, negative 3, 5, but you could really use any multiple of that and that would also work just fine. So this is typically how we calculate the distance between a point and a line. PS is the vector from any point on the line to the point S that's not on the line. And V is a vector in the direction of the line, or a vector that is parallel to the line. I never remember this formula. I couldn't, if you asked me this formula without drawing the picture, I'd be like, there's a cross product somewhere, maybe something else. I have to draw the picture to know what's happening. But once you draw the picture, you're like, oh yeah, of course. I know that sine theta is opposite over hypotenuse, and then the distance is sine theta times the magnitude of the hypotenuse. And then I'm going to throw in a magnitude of the other vector so I can make the cross product happen. All right, let's do the calculation. Because right, there actually were numbers here. It doesn't really matter which order you do the cross product in. If you're looking at the notes on Grant's handout, he actually has written it in the opposite order. That's okay. It doesn't matter, right? Whatever, I mean, it does matter because it does give you a different vector, but we're talking about magnitude here. So that's all right. I think I can erase some stuff. Yeah, let me erase some stuff here just so that we can actually do the calculation on the same page. So let's find the magnitudes of things. So V cross PS, that's going to be the determinant of this matrix, IJK, and then V is, I guess I should write down what the vector V is. So V, I erased my stuff, I'll just calculate it. V is the vector from this point to this point. So 3 minus 2 is 1. Negative 1 minus 2 is negative 3. And 5 minus 0 is 5. That's why you might want 2 points on your line, just so you can remember what the vector is. You could also, you could probably go in the opposite direction and be safe, but it's better to start at the same point here. So yeah, you would probably be fine. So let's see, I'm going to have 1, negative 3, 5, and then my vector PS is going to be, I didn't actually write down what that was either, right? So my vector PS is 1 minus 2 is negative 1I, 2 minus 2 is 0j, and 3 minus 0 is 3k. So negative 1, 0, 3. All right, so it's going to be I times, let's just do the math. So I times the determinant of this 2 by 2 matrix, which is negative 9 minus 0, minus j times the determinant of this matrix with these parts, which is going to be 3 minus minus 5. So 3 plus 5 is 8, plus k times the determinant of this 2 by 2 matrix, which is 0 minus 3. So minus 3. Let me double check to make sure I didn't make a dumb error. It's looking good. So my vector here is, my vector here is negative 9I minus 8j minus 3k. If you look at the notes Grant did, he did the cross product as PS cross V, and he got the vector positive 9I plus 8j plus 3k, because if you do the cross product in the opposite order, you get the negative of the vector that you would have gotten. Either way, though, the magnitude is still the same. Do I have a place to write this? I'm kind of running out of room. The magnitude of V cross PS is equal to the square root of these numbers squared down together. So negative 9 squared plus negative 8 squared plus negative 3 squared. Sorry, I'm out of room. It's equal to the square root of 81 plus 9 is 90 plus 64 is 154. Okay, and then the magnitude of V, let's erase this here. The magnitude of V is just, where'd you go? Here's V. Magnitude of V is the square root of 1 squared plus negative 3 squared plus 5 squared. That's going to be 35. So the distance between this point and this line is going to be the square root of 154 divided by the square root of 35. 154 and 35 both happen to have a factor of 7, right? Because 150 is 140 plus 14. This is actually 35, and you can reduce that to the square root of, I think, 22 over 5. Because 22 times 7 is 154, and 5 times 7 is 35, yeah. Not that you need to do that, but that part is really inconsequential. Okay, so if you are good at remembering things, or happen to be allowed to look up stuff in your book, you probably don't need to draw this picture every time. What I do. So you can make it equal to anything, Mindy. Good point. So here, so again, just to remind everybody, right? If you've got a line, you've got a point on the line, you've got a point not on the line. This point can be any point you want on the line. Usually we do it by letting t equal 0, but you can make any choice you want. Then the way you find the distance from the point to the, the way you find the distance from the point to the line is that the distance is equal to, usually the way the formula is written is as the magnitude of the cross product of PS cross V, although you can do V cross PS, right? Either way, divided by the magnitude of the vector V, where V is any vector in the direction of the line. So V, right, it can be as long or as short as you want, but V is any vector that's in the direction of the line. But so the reason I usually have to draw the picture isn't so much to remember this formula, although it is, but also to make sure that I set up my vectors right? That I'm like, okay, PS is a vector from the line, from a point on the line to the point S that's not on the line. And V is something in the same direction as the line, or something parallel to the line. Let's look at 2 more examples of this. Yeah, we got time. Oh yeah, we got time. So yeah, 2 more examples. I thought I had another example here. Oh, I do. Yeah. So here's number 35 from the textbook, which I don't remember who asked me about this one, but let's go and look at it. We'll leave this up here for a second. So number 35 from the textbook, unless I believe I looked at the current edition of the textbook, but if I didn't, you can correct me on this. Oh, I closed it. There it is. Sorry, yeah. Textbook, where are you? There we are. So here's number 35. I want to find the distance from the point 2, 1, 3 to the line given by, where'd you go, line? X equals 2 plus 2t. Y equal to 1 plus 6t. And z equal to 3. So this is an exercise of being aware of what's happening. Because you could totally do this one and do a lot of work that you don't need to do. So I'm going to pretend like I don't see the thing that you might all see. Here's my line. The direction of this line is 2, 6, 0, right? There's no t there. So it's, you can either write it this way, 2, 6, 0, or you can write it this way, 2i plus 6j plus 0k if you want. And then here's my point P on the line. P can be whatever you want. And then here's my point S, which is 2, 1, 3. Now, here's the thing. If you pay attention, so if you look at this one, if you pick t equal to 0, what do you get for P? Well, if t equals 0, you get x equal to 2, y equal to 1, and z equal to 3. You get the point 2, 1, 3, which means the point that you're trying to find the distance to is actually on the line, which means the distance is 0. Once you see that the point you're asked about is actually on the line, you should just stop and go, hey, buddy, distance is 0. I don't have to do any calculations. You can do the calculations, but it's kind of silly because the vector PS, well, I mean, I guess you could pick a different point if you wanted to. That seems ridiculous. I'm going to say the vector PS is the 0 vector because the distance from P to S is 0. So, I mean, you could pick it. You could pick another point if you wanted to, and you could pick P equal to, say, you could pick T equal to 1 and say that P was the point 2 plus 2 and 1 plus 6 and 3. So then the vector PS is 2 minus 4 is -2. 1 minus 7 is -6. 3 minus 3 is 0. But then when you try doing the cross product between PS and V, well, look, PS and V are in the same direction. They're actually in opposite directions. Okay. But that means the angle between them is 180 degrees, which means the cross product is going to be 0 because sine of 180 degrees is 0. You could also actually do the right. I mean, all this work is, I should have stopped talking about this like 2 minutes ago. All of this work is totally dumb. If you want to do the cross product between PS and V, look what's going to happen. Right? Each of these components is going to be 0. You're going to get I times 0 minus 0. You're going to get J times 0 minus 0. And you're going to get K times negative 12 minus negative 12, which, hey, guess what, is 0. It's 0. So definitely be aware, sometimes the book likes to ask you kind of trick questions and be like, oh yeah, if you have a point, oh, the point's on the line, you're done. Okay, let's do one more real one. So with that problem 35, right, it might have, maybe whoever was asking, I don't remember who was getting stuck just because like it was dumb and it was like, oh yeah, the point is actually on the line, so the distance is 0. But let's look at number 36. It's good to practice this stuff because it can be really easy to like not remember how to do the thing. So let's look at number 36. The point is 2, 1, negative 1. And the and the vector or the line is given by x equal to 2t, y equal to, what do we got here? 1 plus 2t. That's exciting. Not really, I'm just being sarcastic. Y equal to 1 plus 2t. And z equal to, what do we got here? I think also 2t. Yes. Not super exciting. So, I mean, you could, let's try and do this without drawing the thing just to see if we can. So I'm going to pick the point P. I'm just going to let t equal to 0. So P is going to be 0, 1, 0. Okay. And then this is my point S. So I know that the vector PS is just the S coordinates minus the P coordinates. So it's going to be 2i plus 0j minus 1k. And then I also need the vector V. V is just the vector that's in the direction of the line. So just take the components, the coefficients of the t's. 2i, 2j, 2k. And then if we remember the formula, which I only remember because we just literally talked about it and I just erased it, the formula for the distance is going to be the magnitude of the cross product of PS cross V divided by the magnitude of V. Have to do the cross product, okay. IJK, 2, 0, negative 1. 2, 2, 2. I'm going to write out the long way this way just so everyone remembers what it looks like. So this is going to be, I wonder if there's a formula for like the magnitude of this without, I mean, no, there's probably a formula that's not nice to remember. So it's going to be I times the determinant of 0, negative 1, 2, 2, minus j times the determinant of 2, negative 1, 2, 2, plus k determinant of 2, 0, 2, 2. That's going to be I times 0 minus 2, so 2, minus j times 4 minus 2 is 6, plus k times 4 minus 0. And then I want the magnitude of that. So the magnitude of that is just the square root of the square, sum of the squares of the components. So it's going to be the square root of 2 squared plus negative 6 squared plus 4 squared divided by the magnitude of V, which is square root of 4 plus 4 plus 4. So it looks like we end up with the square root of 56 over 12, which you could certainly reduce to the square root of, I don't know what 56 divided by 12 is, 14 over 3. That's the distance. I still think it's probably worth our while to usually draw the picture, right? So just to kind of make sure everyone's cool with this, right? picture. Here's your line. Here's your point P, which is, we said 0, 1, 0. Here's your point S, which is 2, 1, -1. This is your PS. Here's your vector V, which is 2I plus 2J plus 2K. I just think I think we should draw this. Like I would probably draw this every time I was finding the distance between a point and a plane. A point and a line. Okay. Sure. I'm just trying to look and see if there's any ones from points to planes. We'll do that in a second. So there is another question that someone else was asking about, which is question, I think, 63. It's to find the equation of the line where two planes intersect. Planes don't have to intersect. So just like, actually very much just like lines. So just like we can see that two lines are parallel if they are multiples of each other, planes are parallel in the same sort of way. Meaning, just for example, this plane, 2x minus 3y plus 6z equal to 11, and this plane, negative 6x plus 9y, I multiply by negative 3, minus 18z equal to 5. These planes are totally parallel because the coefficients of x, y, and z in this equation are exactly multiples of the coefficients of x, y, and z in this equation, or vice versa, whichever way you want to say it, right? Here, all these are multiplied by negative 3 to get to here. So these two planes, definitely parallel. And I will point out, if this instead of 5, if this were negative 33 instead, then the planes would be parallel, but they'd actually be the same plane because literally it's just this equation, whole equation multiplied by negative 3. So just like lines are parallel, right? If they are the same slope but have a different y-intercept, these planes are parallel if they have the same slope, but like they're equal to a different thing over here. So yeah, the planes are parallel. But if we have some not parallel planes, we want to find out the equation of the line where they intersect. So let's look at some not parallel planes. Unlike with lines, if two planes aren't parallel, they do have to intersect, right? You can't have two planes, right? Planes take up whole 2 dimensions each. So right, if they're not parallel to each other, they're going to cross at some point. I think Morgan just joined us. Morgan, I'm literally just talking about problem 63, which I think you asked about, but if it wasn't you, that's also all right. So yeah. Cool, awesome. So I was just talking about how planes are parallel if all their coefficients are the same or multiples of each other for x, y, and z. And now we're going to say these two planes for problem 63, x minus 2y plus 4z. Why am I looking over there? I wrote it down over here because I was smart. Oh, or did I? I wrote it down somewhere. There we go. Right here. Okay. So here's our planes. X minus 2y plus 4z equal to 2, and x plus y minus 2z equal to 5. So we want to find, well, first of all, notice they're definitely not parallel, right? This line, the coefficients here are not all the same multiple of the coefficients here, vice versa. So we want to find where they intersect. So here's the way we typically do this. I'm going to try and draw a picture. It's probably not going to be very good. You guys will see. Eventually this picture will make some sense to you, maybe. Like, sure, James, whatever you say. Yeah, I'm like, maybe? I feel like I'm missing some. Oh, I know I'm doing it. Okay, yeah. Yeah, my 3D pictures always come out kind of wonky. Not always, but a lot of the time. This is what's coming on like this. Yeah. Let's do it like that. There's a little bit there. Let's make this a little more slanty. hopefully you can kind of believe that this line here is where these two planes are intersecting. That seems moderately reasonable. Okay, so here's the idea. To find the line, or at least the direction of the lines where two planes intersect, well, what we're going to do is we're going to take the normal vectors to each plane. So if two planes intersect, then if I take the vector that's, and this is where the picture is going to start to fall apart maybe. So if I take, like, say, oh, let's just draw it right here. So for this plane that's flat, its normal vector looks like this. And for this plane that's slanted this way, its normal vector looks kind of like this. And if we take the cross product of those two vectors, so I do, let's do the cross product of this one, cross product of this one to that one. Sorry, I know you guys can't really kind of tell where I'm pointing, but basically if you cross this one to this one, the vector that's normal to both of them is in the direction of the intersection of the two planes, which is kind of cool, right? It's perpendicular there and it's perpendicular there. That's something that's always true. If you take the normals to each plane and you cross them together, you get a vector that is in the direction of their intersection, right? Because basically, if you take this line in this plane, well, yeah, that's the word I should be saying. The line is in both planes. So the normal vector to a plane is normal to any line in the plane. So this vector that's normal to this plane is normal to that line that's in the plane. And this vector that's normal to this plane is normal to the line that's in the plane. So that's how we find the direction of the vector. And we know how to find the normal vectors. The vector that's normal to this line is 1i minus 2j plus 4k. And the vector that's normal to this line is 1i plus 1j minus 2k. And the vector that's normal to both of them is the cross product. So let's call it v. So v is going to be, it doesn't matter which way you go, n1 cross n2. So that's going to be I, j, k, 1, negative 2, 4. And then 1, 1, negative 2. Oh yeah, I remember there was an interesting little kind of twist on this problem at the end, which was confusing me just a little bit. So to get this here, let's see. We're going to get I times, let's just do it this way, 4 minus 4 minus j times 1 times negative 2 minus 4 times 1. And then finally k times 1 minus minus 2. So I'm getting 0i minus j times minus 6 is 6j, and plus k times 3 is 3k. Okay, so there's the direction of my line. But that's not, to find the equation of the line, I need the direction and a point, right? Just like for 2 dimensions, I need a slope and a point. I need to find a point. So I need to find a place where these two lines intersect. Okay, sorry, these two planes intersect, apologies. So to find a place where two planes intersect, we typically just take one of the variables, set it equal to a number, and solve for the other two. Right? The problem here is I have 2 equations and 3 variables. I would like to have one less variable so that I can actually solve this thing. And the mistake I was making when I was first trying to do this was I was setting x equal to anything. So I set x equal to 0, and here's the problem. And you might already see this, you might not. My direction is 6j plus 3k. There is no I component, meaning the x value is never going to change. Right? If you write the equation of a line as a point plus this vector, the j and the k, meaning the y and the z components, actually change as you let things go in any direction, but the x component isn't going to change. So when I guess x equal to 0, let me just show you what's going to happen. If I set x equal to 0, I got problems, because then I have negative 2y plus 4z equal to 2. and y minus 2z equal to 5. And you might notice that these coefficients are multiples of these coefficients, right? If you multiply this whole thing by -2, you get this whole thing. But that means these lines are parallel, which means these lines don't intersect, which means x equals 0 is a place where these planes don't actually intersect each other. So the real kind of thing to think about here is that basically, if the direction of your vector is missing one of the components, don't pick that component to equal just any number. Pick anything else. So let's pick z equal to 0. If we pick z equal to 0, we're left with x minus 2y equal to 2 and x plus y equal to 5. I personally am a fan of solving for one of these and plugging into the other, but you guys might like the thing where you like do this equation minus this equation, which looks very convenient the way I set this up. So this minus this, x minus x is 0x, negative 2y minus y is minus 3y, and 2 minus 5 is negative 3. So y is going to equal 1. And then if y is equal to 1, well, then I can solve for x. X minus 2 equals 2, so x equals 4. And x always equals 4, right? No matter what we picked, in this particular example, since our vector doesn't have an I component, x is always going to be the same. So our answer here for our line is you can either write the line as the point 4, 1, 0 plus the vector 0, 6, 3. Or you could write it kind of the more standard way of writing it, that x equals 4 plus 0t, y equals 1 plus 6t, and z equals 0 plus 3t. That would be the parametric equation of your line. I would say the easy part here is actually finding the direction, right? Taking the normal vectors and taking their cross product, that gives you the direction. The harder part is actually finding the point, a point where the lines intersect. Planes, finding a point where the planes intersect. So to find a point where planes intersect, you do kind of have to be like, oh, I'm going to just set one of the variables equal to whatever I want. And then just don't make the dumb mistake of setting a variable that happens to be equal to a constant equal to not that constant. Basically, don't pick x, pick something else in this particular example. So once you've said, okay, I'm going to let y equal 5, then you can find the rest of them. And it will work. In fact, let me just show you. We could have picked y equal to, let's not pick 5 just because it's probably going to be lame. Let's pick y equal to -5. Sure. So let's say we did that instead. I just want to show you that usually you can choose just about anything. So if instead for these equations I picked y equal to -5, I would have x plus 10 plus 4z equal to 2. And I would have x minus 5 minus 2z equal to 5. And then I can still do the thing where I subtract them. It's kind of looking terrible. If I subtract them, I get 10 plus 5, 4z plus 2z equal to 2 minus 5, which is -3. Subtract 15, 6z equals -18, z equals -3. You guys are like, okay, well, that's not the same. You're right, it's not the same point. That's okay. So now my point is going to be, sorry, y equals negative. So the point's going to be, wow, z is -3. Y is, we said -5, right? I said -5, this is a -5. And x, if I plug back in z equal to -3 and y equal to -5, I'm going to be left with, sorry, I know it's a lot of braining right now. X, I'm plugging in -5 for y, so plus 10. I'm plugging in -3 for z, minus 12 equal to 2. Solving for x, I still do get 4. So alternatively, instead of using this, we could have said, or we could do the point 4, -5, -3. That is also a perfectly valid option. And really, it's just -1 away, right? If you take this and you set t equal to -1, you get 4 minus 0, 1 minus 6, 0 minus 3, which gives you the 0.4, -5, -3. So that is also a point on the line. So your parametric equation can have any point that's on the line. So, and which means your answers might differ from each other if you were looking at that. Yeah. But yeah, finding the point's kind of a pain in the butt. I feel like I definitely, so let me talk about, think, distance from a point to a plane. Point to a plane, line to a plane. Let me look. See what we got here. Point to a line, we did. Point to a plane, yeah. So here's what I would try to remind you all, even though you haven't seen it yet. 13.2, I don't think I'm ready to get to chapter 13 yet, Morgan. So let's talk about the distance from a point to a plane. But I could take a look at it in office hours, which I have right after class if you want. So yeah, so point to a line, cross product. Point to a plane, dot product. Let's take a look at the picture. I want to find the distance from the point S given by 2, 1, 6. Ooh, 2, 1, comma 6. I think my writing skills are definitely decreased. And the plane given by the equation 4x plus 6y plus 3z equal to 12. 4x plus 6y plus 3z equal to 12. Okay. And I want to find the distance from the point to the plane. So let's try and draw a picture here. So here's my plane. Having a good old time being a plane. And we're going to find a point in the plane. And then here's my point S, not in the plane. And I want to find this distance here. And just like before, we're going to think about, I always draw this differently than other people draw it. Yeah, because no, that's fine. Yeah, okay. Yeah, I'm going to draw it the way I like to draw it. I'll draw it both ways. Maybe I'm wrong though. Maybe I'm silly about this. Okay, we need a point. Let's find the point before I do anything super crazy. So this point here, you can pick any, like basically just pick a point that works. So I'm going to pick the point 0, 0, 4. That'll work. But you can pick the point 3, 0, 0 or 0, 2, 0 or something else less nice. So I can see that, yeah, I can see that I'm making a bad choice here because I see the problem. Yeah, so the way I've drawn this picture is not good. And that's always the problem. I always have a problem with this because the reason here is that I don't know what this point is and I need to know what this vector is if I'm going to do something. So yeah, I know I was, yeah, okay, so that's not the way to do this. That's all right. Hopefully you guys, sorry if you copied that down. Yeah, this is where I struggle. Try to find the point, you actually want to find a point in the point. And then from the point in the thing you found, you want to draw the vector that is normal to the plane. So we know that is normal there. And we know what the normal vector is. The normal vector is just take the coefficients. It is 4i plus 6j. Normal vector to a plane, always nice and easy. And then we want to know, well, if I draw this here, I want to know what this distance is. This pen is like, looking like my hands, looking like trash. Okay, so we want to know this distance. We're looking at this angle here. So we can say, well, look, if we use cosine of theta, we can see that cosine of theta is going to be adjacent over hypotenuse. So it's going to be the distance we want over the magnitude of the vector PS. I'm using office hours from 3 to 4. So you're welcome to come by close to the end if the beginning part doesn't work for you. So again, we're going to do the same sort of thing. We try and solve for D. So we see that D is equal to the magnitude of PS times cosine of theta. And then we're going to slap on the vector that we want. So, right, so we've got PS. We also need this vector. So if we do, right, because theta is the angle between the normal vector and the vector PS. So if you do the magnitude of PS times the magnitude of n, well, we can't just multiply by the magnitude of n. We're going to multiply by the magnitude of n and also divide by the magnitude of n. Well, then this numerator quantity is the dot product between this vector and that vector, right? The magnitude of a vector times the magnitude of the other vector times the cosine of the angle between them is the dot product of the two vectors. So this is actually equal to PS dotted with n. We use an absolute value here. So I know an absolute value symbol looks a lot like a magnitude symbol, but right, the dot product can be positive or negative, but we only want distances to be positive. So we're going to say it's the absolute value of the dot product divided by the magnitude of n. Not terrible at all. So now, let's see, PS, the vector PS in this case is 2 minus 0, 1 minus 0, 6 minus 2. So that's going to be 2i plus j plus 2k. And then this calculation here, let's see. PS dotted with n is going to be 2 times 4 plus 1 times 6 plus 2 times 3. So that's going to be 8 plus 6, which is 20. And the magnitude of n is the square root of 4 squared plus 6 squared plus 3 squared. So this quantity here is going to be the absolute value of 20, which is 20, divided by the square root of 61. And that's how you find the distance between a point and a plane. So these formulas, I mean, they look kind of similar. I couldn't memorize this if maybe if my life depended on it, but like, right, if something important that wasn't that important to me depended on it, I probably couldn't memorize this because it's just not there. But I could definitely draw the picture every time. Well, maybe not for this one, right? For this one, I have to think about it. So for this one especially, right, it is a little confusing because, right, you're trying to find this distance. I often want to draw it like this because I'm not careful, but you don't. You want to draw it. So from your point that's in the plane, you want to draw your vector PS, and also from that same point, you want to draw the normal.